Welcome to our next unit in AP Chemistry on kinetics of reactions. In this unit, we're going to be looking at the progress of a reaction from start to finish and all the steps along the way, so not just looking at the beginning and the end. So kinetics studies the rate at which a chemical process occurs and sheds light on the reaction mechanism. And the reaction mechanism is the actual step-by-step process for a reaction. This is different than when we looked at thermodynamics, because thermodynamics, all it was concerned with was the beginning, or the start, and the end. They weren't concerned with what happened in the middle, but just the difference between the beginning and the end, difference between products and reactants, that sort of thing. So when we talk about rates of reaction, we are talking about a change, this is very important, a change in concentration of a reactant or product per unit of time. So looking at the units here, a concentration, so it's kind of like a slope. The concentration of a substance at a final time versus an original time, and then the time subtracted. So if we're looking at concentration, the concentration will be given in molarity. Okay, so the change in concentration will be molarity, and the change in time is usually in seconds. So when we're talking about reaction rate, you will see the rate expressed in different ways. You might see it expressed as molarity over seconds. You might see it expressed as molarity times second to the negative first power. You might see it as moles over liters times second. You might see it as moles times liters to the negative first times seconds to the negative first. So it just depends on what you're reading, like the format that they use for the unit of rate. When we look at reaction rates, we can graph the change in concentration per unit of time and measure the disappearance of reactants. So in this particular case, that would be the NO2, the green line, and we can measure the appearance of products, which would be the nitrogen monoxide and the oxygen. The rate of the disappearance of reactants and appearance of products are proportional stoichiometrically. So what that means is if we look at the coefficient of the NO2 and the coefficient of the NO, they're the same. And if you look at the lines, the curves for green and blue, they mirror each other. The rate of disappearance of NO2 is equal to the rate of appearance of NO because they have the same coefficient. And it also then would make sense that the rate of appearance of oxygen would be half that, the rate of appearance of the NO, because its coefficient is half that of the NO. You can calculate the rate of a reaction at a given moment by calculating the slope of a tangent line to a particular point on the curve. And you can see that where the black triangle is, you have your slope that you can calculate, right? Difference in y over difference in x. But if I calculated the tangent, the slope of the tangent at this point further along the way, you can see, I mean, that's obviously not a perfect tangent or anything, but you can see that the slope is different. In most reactions, the rate of the reaction changes as the reaction proceeds. You could see at the beginning of this reaction, the rate of the disappearance of NO2 was very rapid, and eventually it slowed down as the NO2 was being used up. So what you need to remember here is that the change in concentration of NO2 and over the change in time, that rate is not a constant. So this is a data table, experimental data, for that exact same reaction we were looking at. So we have the time involved, and then we have the concentrations in molarity for the reactant and each of the two products. So what you can see from this data, looking just at the NO2, is as time progresses, at first, our concentration drops pretty rapidly, and then the concentration changes less and less as the reaction proceeds. And conversely, with the nitrogen monoxide and the oxygen products, at first it jumps up pretty rapidly, and then it kind of tapers off in how it accumulates over time. Also to make note of here, the difference between the nitrogen monoxide and the oxygen concentrations as they accumulate, it makes sense that the concentration of the oxygen would be about half of the concentration of nitrogen monoxide at any given time because the oxygen is not accumulating as fast. It's accumulating half as fast as the nitrogen monoxide. And again, here's just another graph of that same reaction that you can see if you were just given the chemical equation and these lines weren't labeled with the substances, based on the coefficients in the balanced equation, you should be able to identify which substance is which curve belongs to which substance, based on if they mirror each other or not. So the NO2 and the NO mirror one another perfectly because the disappearance of nitrogen dioxide is equivalent, I guess, and opposite to the appearance of the nitrogen monoxide, and the oxygen is appearing half as rapidly. So you can calculate the instantaneous rate, the value of a rate at a particular time, by computing a slope of a tangent line to that curve at a particular point. This comes up on free response. Sometimes you can't just, if it asks how can you calculate the instantaneous rate at, let's say, time equals 60 seconds, you can't say find the tangent. You have to say calculate the slope of the tangent line at 60 seconds, because it's the slope that gives you the rate, because it's the difference in y concentration over the difference in x time. When you are talking about the progress of a chemical reaction, we can write things called rate laws, and we're going to be spending a few days on this concept. So reactions are reversible. Whether or not they're thermodynamically favorable in the opposite direction is a different story. But as products accumulate, they can react and allow the reverse reaction to proceed. But for us right now, we are just concerned about right after a reaction starts and product concentrations are negligible, we can come up with something called a rate law. A rate law is an expression showing how the rate of a reaction depends on the concentration of the reactants that we have. So we're not concerned with products at all. We're just concerned with how will the rate of a reaction depend on the concentration of reactants. So this would be an example experimental data. So somebody ran 6 different experiments using varying concentrations of ammonium ion in solution, varying concentrations of nitrite ions in solution to cause a reaction. And the initial rates were observed after data was plotted. So we can see how changing the concentration of the ammonium ion while we hold the nitrite constant affects the initial rate of the reaction. So what we see here is that when we double the concentration of ammonium, we also double the initial rate of the reaction. We're holding the nitrite constant as like a control. We could also then examine how altering the concentration of the nitrite while holding the ammonium constant would alter the initial rate of reaction. So we doubled the concentration of nitrite, we also doubled the rate of the reaction. So what we know for this particular process is that the rate of the reaction is directly proportional to the concentration of ammonium, and the rate of the reaction is also directly proportional to the rate of the nitrite. So it's proportional to both. So when we write a rate law equation, this is the form that it would take. Rate, again, that would be in molarity over time, equals K, which is called a rate constant, which I'll talk about, times the concentration. When you see a substance in brackets, that means molarity, the molar concentration, raised to a particular power, times the molar concentration of nitrite raised to a particular power. In this case, the N is not equal to number of moles. It's called something called an order that we'll talk about. So that is called a rate law. A rate law is rate is equal to lowercase k, which is a rate constant, times the concentration of each of the reactants raised to a particular power. So again, this is just the same equation. K is a rate constant. The rate constant is a value that can only be determined experimentally. We don't have a chart of these. You'd have to have experimental data and calculate it. N is the order of the reaction with respect to either the NH4 in this case or the NO2. This can only be determined from experimental data. It can be an integer, 0, 1, or 2 is really all you guys are going to see, possibly a fraction, but I haven't seen any of those in AP. We never include products in our rate law because we're looking at the initial rate of a reaction when the concentration of products are negligible. So for this particular reaction, if we were to write the rate law for the decomposition of nitrogen dioxide, automatically we're ignoring the products. So the rate of the reaction is equal to a rate constant times the concentration of that reactant raised to a certain power. And right now, based on just this equation, we cannot tell the order of the reaction with respect to NO2 from a balanced equation. The only way to get this is from experimental data. So you can only get K through calculation, and that would come from experimental data. You could only get the order of reactant from experimental data as well. We have different types of rate laws. The first type we're going to look at is called a differential rate law. Usually it's just known as a rate law. This relates the rate of a reaction to the concentrations of the reactants. The other type of rate law we'll be looking at is called an integrated rate law. So here comes some calculus. JK, I'm not doing calculus, but it's called an integrated rate law. It shows how concentrations depend on time. Okay, so depending on what a question asks, you'd want to use a particular form of the rate law that would best suit your needs. And it's actually easy to get from one to the other because your reference sheet provides you with integrated rate laws that we'll discuss later on. At this point, all we're really going to look at are how to come up with and then use the differential rate laws, which relates the rate of a reaction to concentration. So again, we're just using reactants, moving on. So like I said before, depending on the data that we have available to us, we'd either choose to use a differential rate law or an integrated rate law. Knowing the rate law for a reaction is important because we can usually infer individual steps of a reaction from that, which comes later in this unit. So what we're going to look at for this differential rate law is we're going to use experimental data to determine the power to which each reactant concentration must be raised. So we want to figure out the order of each reactant. And you're going to get data tables in your questions that will help you do this. So we're going to look at zero order reactions, first order, and second order. So in a zero order reaction, doubling the concentration of a particular reactant has no effect on the reaction rate. So the form of the differential rate law would be the rate of the reaction is equal to the rate constant times the concentration of that substance raised to the 0 power. Now, anything raised to the 0 power is 1, so the rate would just be equal to the rate constant. If you doubled the concentration of A, this would still be 1, so it's still going to be equal to the rate constant. If you plotted a graph, see how this graph is different than the ones that we were looking at where we had these curves, the rate was changing over time. If we plot the concentration versus time, we have a constant slope here. So the rate of reaction, so the rate is the change in concentration delta Y over delta X, is not changing as the concentration changes for a zero order reaction. So it kind of just chugs along. A first order reaction is when you double the concentration of a particular substance and it would double the reaction rate as well. So multiplying the concentration by 2 would multiply the initial rate by 2. For a second order reaction, if I multiply the concentration by 2, it would actually quadruple the reaction rate. So a zero order, changing the concentration, there's no rate change. For a first order, If you double the concentration, you double the rate. And for a second order, if you double the concentration, you quadruple the rate. You're raising it, you're squaring it. Okay, so in this particular example, we have a reaction given to us, evaluation of reaction rates at N2O5 concentrations of 0.9 and 0.45 yields the following data. So what is this telling us about the N2O5? So we look at the information here. When we doubled the concentration of the N2O5, what happened to the rate of that reaction? Well, the rate of the reaction is doubled as well. So what's the pattern that we looked at? If we double the concentration and we double the rate of the reaction, that means that the rate of reaction is dependent on the concentration of N2O5. It's a first order reaction. The reaction is first order with respect to the concentration of N2O5. It has nothing to do with the coefficients, because the coefficient for the N2O5 in that equation was 2. It has nothing to do with the coefficients. If there were multiple reactants in this equation, each can have its own order, and you would have more data for that. The overall reaction order would be the sum of those exponents. This is just a summary of those 0, first, and second that we looked at before. So let's look at some units for K. So this is just giving you an introduction to this whole concept of a rate law without a lot of examples. So if the order of your reaction is 0 order overall, and we said that if we had a concentration raised to a 0 power, that's just 1, you absolutely need to either know how to derive or just memorize the units for the rate constant for the particular order of a reaction. So if you're at a 0 order reaction, the unit for rate is molarity over seconds, right? Or molarity times second to the negative first power. So if we're looking at a 0 order reaction and the rate is equal to the rate constant, then the units for the rate constant also have to be molarity times second to the negative first power. If you're looking at a reaction that is first order, again, the unit for rate is molarity times second to the negative first, okay? Well, what's the unit that's inside, that corresponds to the number inside this bracket? The number inside this bracket, that's concentration, it's molarity, so that is M. So what does the unit of the rate constant have to be so that when I put these units together, I end up with the unit for rate? Well, what's missing? I'm missing seconds to the negative first power. So for a first order reaction, rate, which is molarity times second to the negative first, equals K, a unit of second to the negative first, times molarity, the concentration raised to the first power. For a second order reaction, again, the rate unit we're looking at is molarity times second to the negative first. Now, if we have A is molarity, and we square it, that's molarity squared for the unit for this component right here. Well, what does the unit of K have to be so when these units come together, they give us molarity to the first power times seconds to the negative first power? Well, the unit for K has to include second to the negative first, and it also has to include molarity to the negative first to cancel out one of those molarities from the molarity squared component. A third order reaction, again, rate is going to be molarity times second to the negative first. Well, if I take molarity and cube it, what does the unit of K have to be? So when I put everything together, I get molarity times second to the negative first. Well, it has to be, the unit for K has to be molarity to the negative second power, because that will offset 2 of the 3 molarities, times seconds to the negative first power. you'll see as we do more of these problems how many times they ask over and over again, what is the unit for K? What is the unit for K? What is the unit for K? So being able to derive that unit or just memorizing the units can really be helpful. So what we just looked at was an introduction to kinetics in terms of understanding how the rate of a reaction works, how the rate of or the reactants decrease over time, the products increase over time, and how we can use graphs to analyze this and how we can use experimental data to see how the rate changes with concentrations of reactants.